Good morning. This is our last lecture. We've got an exam on Friday, and that starts at 9 a.m. I'll send out an email reminder. It starts at 9 a.m., so you have plenty of time to finish before my next class, my 11 o'clock class. Okay, we are going to do a very light treatment of AC circuits. Because a couple of reasons. One, we're just out of time. Two, even in a normal quarter where we'd have another week, there really isn't enough time to do it right. At AC circuits, there's a lot going on there. We have to use phasor diagrams and things to solve them. And there's a lot going on. I say, let's just get the fundamentals. Let's just kind of get a conceptual understanding of what's going on. And if you really have an interest in this stuff, we have a whole circuits class, Engineering 37. Take that and get a good treatment of circuits. Okay, so last time we talked about the fact that we've got, and with an LC circuit, it acts like a harmonic oscillator. No, I don't teach Engineering 37. I don't have an engineering degree. LC circuits, inductor and a capacitor, right? Oops. Okay, we talked about the fact that if we start out with this circuit with the capacitor charged up, all the energy's in the capacitor. We close that switch. The capacitor discharges through the inductor. At some point, the capacitor has zero energy, zero charge stored on it, and the current in the circuit hits its maximum value at that point, and the inductor has maximum energy stored. And then it goes back to the capacitor, but it's charged in the opposite orientation. So the energy just oscillates back and forth like this, just like a pendulum or a mass on a spring going back and forth. The potential energy, kinetic energy, potential energy, kinetic energy with a mass on a spring or a pendulum. Here it's electrical energy, magnetic energy, electrical energy, magnetic energy. And because there's no resistance in this circuit, it'll oscillate back and forth forever. We know that there's a frequency of oscillation, 1 over the square root of LC. Oh, come back, one note, come back. Okay, we're back. Now, if you put a resistor in there, then we have what's called a damped oscillator. Usually we'd have a power source, but not always. All right, so if we have, let's start off with what we were just talking about, our LC circuit. And what's an analogy would be something like this, right? A mass oscillating back and forth on a spring, frictionless surface, right? If we add in a resistor, now we have what's called a damped so something like, well, the one above it with friction, right? All we have to do is add friction in there, and that would be the same thing. Or if we want to make it a little more obvious, something like this, right? A mass on a spring with in a beaker of water, right? That would be obvious that that's damp. That's like taking air resistance to the extreme, right? Lots of resistance as that moves up and down in that fluid. And if we have a power source in there, then our circuit becomes a driven and that would be kind of like this. We'll take that same example. We've got our fluid here, we've got our mass on a spring, but now it's connected to a wheel that's spinning around, right? We're doing this basically, right? We're driving it, we're moving the top up and down, right? Driving it up and down a little bit. This is a driven, damped oscillator, harmonic oscillator. Oops. All right, so the driven damped harmonic oscillator is kind of like pushing on someone on a swing. If you push at just the right interval, at the natural frequency of the oscillator, right? A swing has a natural frequency it wants to oscillate back and forth at a certain time it takes to complete one cycle, right? And if you push at just the right time interval where your pushes coincide with its cycle, then the amplitude gets bigger and bigger and bigger, even if your pushes aren't very big, right? They keep adding up and they get bigger and bigger. But if you push at the wrong frequency, then sometimes you're pushing with the oscillator, sometimes you're stopping it, and nothing really happens. It's just kind of chaotic motion. It never really oscillates very much in terms of the amplitude of oscillation. If you push with the natural frequency of the swing, the amplitude becomes large. So our circuit is the same way. It's the same way. If the EMF source, if that sine wave here, this one, if that sine wave that we're pushing with, the frequency that we're pushing with the EMF source matches the natural frequency of the circuit responds with a large amplitude, large current. With the natural frequency of the circuit. What is the natural frequency of the circuit? 1 over the square root of LC. That's a square root sign. The circuit responds with large current. So if we were to plot the current versus the frequency that we're driving this at, we get something like this. At the natural frequency, omega naught, you get maximum current flow. And as R becomes smaller, the peak becomes higher. And what is omega naught? It's the natural frequency it's 1 over the square root of LC. All right, one example of this is a metal detector. You can set up a circuit that has, you're driving it with a frequency that the circuit oscillates at. So you have an LRC circuit like this. And you're driving it at the natural frequency of the circuit. So you get this big response, you're getting a big current flowing. And if a piece of metal, iron, with iron in it, goes over your inductor, so your inductor, let's say you have one of those metal detectors that you see somebody at the beach walking around with it, right? So you've got your has a loop on the bottom, right? That's the inductor. Now it's perfectly clear, right? You got somebody walking around the beach with one of those metal detectors, and it usually looks like a ring at the bottom. Well, that's the inductor. That's the inductor in the LRC circuit. It's a coil of wire. And what happens to the inductance when we put an iron core in the middle of it, right? What we talked about electromagnets, we put an iron core in the middle of the electromagnet, and it's much more effective. It intensifies the magnetic field in there. Well, if you take a coil of wire, an inductor, do I have my circuit here? This is the circuit that was used in the lab. And this is the inductor that we used, and it's marked over here, 8.2 millihenries. But over here, there's an iron bar. And if you take that iron bar, you know what that's for? You stick it in the hole there in the inductor, and you've just changed the inductance quite a bit, because it responds very differently now to current. The inductance is very different now. So you've got a circuit that's tuned very nicely to a specific inductance. And now all of a sudden there's a little chunk of metal inside your inductor that changes the inductance a little bit. What happens to the current in your circuit? It drops way down. You can detect that. And so that's how a metal detector works. Yes, I don't know why we have so many different names for a coil of wire. A coil, a solenoid, an inductor, they're all basically the same thing. All right, so metal detectors are one example. Actually, well, the magnetic field, from this coil of wire, let's just draw a coil of wire here. Right, this is the inductor. Right, so as you drive it, what happens? It generates a magnetic field that looks like this, right? At one instant, and then it's changing. So if you have a piece of metal underneath here, if you have a chunk of metal here, then it's possible that the domain alignment there would, it would have to be close enough that the magnetic field from the piece of metal influences the loop, right? It has to be close enough that it influences the loop. Oh, the other thing is like a radio signal. You're in your car, you tune the knob, you turn the knob to tune it to a specific radio station. You can hear that radio station. You turn it a little bit to a different radio station, you hear a different radio station, right? How does that work? Well, with the older ones, analog electronics, you had a tunable capacitor. A capacitor where the plates were aligned, and as you turn the knob, the plates overlap more or less. You're changing the area, you're changing the capacitance. So as you tune the radio to different stations, you're changing the capacitance, which changes the resonant frequency of the circuit. Because your antenna on your car is getting hit with every frequency, right? Every radio station is blasting their signal, every frequency is hitting that antenna. but you only want one of those frequencies to be amplified and make your radio play. And they're all being used when we live in a populated area like the Bay Area. I bought one of these gizmos. This was a while back. I don't know, 10 years ago. I had a iPod and I wanted to play it in my car, and there was no auxiliary input or anything there, no Bluetooth connection. So what you could do, you could buy a little gizmo that you plugged your iPod into, and it would play it over a radio signal to the radio of your car. But you had to find a frequency that wasn't being used. Good luck in the Bay Area finding a frequency that isn't being used. They're all being used. Maybe I could find one at home that wasn't being used, but by the time I got to work, it was being used. Yeah, it didn't work very well here. Now, maybe if you're driving down the middle of I-5, going to Southern California, yeah, that I'm sure you can find chunks of radio station, frequencies that aren't being used by the local radio stations, and use something like that. Okay, let's take a step back. And do a problem with LC circuits. Have we done this problem? Oh, we did this problem last time. Good. Let's talk about in the AC circuit here. So I've sort of jumped ahead and put in all these different elements, right? The resistor, capacitor, inductor. Those are our three components that we know about right now. But let's look at each one individually and think about what they're doing to the circuit. Now our power supply is putting out a sine wave, okay? That's what AC circuit is. It's putting out some kind of a oscillating signal, like a sine wave. And we know that the voltage across the resistor is IR. Resistance is caused by the flow of charges through a material and how they collide with the atoms and molecules that make up the wire that the charges are moving through, right? Electrons need to move through a wire, and if they collide with one of the copper atoms that makes up the copper wire, then they get slowed down a little bit, and then they have to get going again, and they collide with something. It doesn't matter whether we're driving this at a low frequency, at a high frequency, the collisions, that mechanism of restricting the flow of charges is the same. It's not influenced by the frequency that we're driving our circuit at. So at any frequency across, from zero frequency over here, what is zero frequency? DC, right? Just hooking up a battery or a DC power supply. all the way up to really high frequencies. It doesn't matter what frequency we're driving this at. Resistance is resistance. It doesn't change. This is a flat line. An inductor in our AC circuit it also, what's the word I'm looking for, impedes the flow of electrons in a circuit. But the mechanism is very different. When the frequency is low, when it's zero, what effect does this inductor have on the flow of charges? Yeah, none. None, just the resistance of the wire, right? That's all. The inductance doesn't do anything. So as we crank the frequency up and the signal starts to change, it's that changing current that causes the inductor to fight the change and push back. And that acts like kind of like a resistance to the flow of current. It makes it harder for our power supply to run current through the circuit if we've got something that's always fighting the change that you're trying to create. But we don't call it resistance because resistance we think of as this collisions with the atoms and molecules that make up the material that we're pushing our electrons through. So we have a different name for it. We call it reactance. And we use this Greek letter chi. So it's like like resistance, but it's how much does the inductor impede the flow of electrons in our circuit. And instead of V equals IR, what we say is V is I chi. So if we plot this, what happens? This is not constant omega or F. As we change the frequency, the effect that the inductor has on the flow of charges changes, right? It's not constant. It turns out we know it's zero, right? We know it's zero. When the frequency goes to zero, it has no effect on the flow of charges. It turns out it's linear. Okay, so what is it? It's where am I? It's omega times L. It's linear. One more, right? We've got a capacitor. And we've talked about this before. When we have DC, if our frequency goes to zero, we want to know, what does the reactance do? At zero, a DC source, a battery, what does this look like? What is the capacitor like for a DC circuit? We're going to flow any charge through there? No. It acts like an open circuit because it is an open circuit, right? For a DC source for zero frequency, it's an infinite resistance. So this has to go to infinity here. As we turn the frequency up, we can flow a tiny bit of charge, right? Because those capacitor plates, it's like a reservoir of charge. We can flow a little bit of charge until the reservoir fills up, and then we can't flow any more charge. And if we go faster, we can flow a little bit, and then by the time the capacitor is pushing back, preventing charges to flow, we flip and we start to charge it, flow in the other direction. And by the time it's pushing back, resisting the flow of charges, we flip. And the faster we're flipping it, the less effect the capacitor has on our circuit. You kind of grasp that? So as the frequency goes to infinity, the capacitor looks like a short. It has almost no effect on our circuit as the frequency gets faster and faster and faster, because you're switching so fast, the charge doesn't have a chance to build up on the plates of the capacitor. It starts to build up, but before charges really build up and it starts to impact the flow of charge, you flip it and you're running it in the opposite direction. So this looks something like this. It's a 1 over omega. Chi C is 1 over omega C. We've done a little bit of this already where we've said, what happens, what does our circuit look like the instant the switch closes or after the switch has been closed for a long time? What does that mean? When the switch has been closed for a long time, we're at the zero frequency limit. We're saying, what does our circuit look like when the frequency goes to zero, right? When nothing's changing. And what this is a battery, it's sort of DC circuit with a switch, right? And when that switch, the instant the switch closes, that's like an infinite frequency. It's really high frequency. We went from nothing to something. That at that instant, it's a really big frequency. So when we're talking about a circuit with a battery and a switch with capacitors and inductors in it, we can replace the inductors, right, with a short when the frequency is low, when the switch has been closed for a long time. And we can replace the inductor with an open circuit. We can just remove the inductor the instant the switch is closed. It acts like an infinite resistance. So we do the same thing now, but we look at it as an AC circuit with a frequency that we can adjust. So let's take a look at this example. We've got a circuit that looks like this. And we want to know, what does this circuit look like in the high frequency limit as the frequency goes to infinity? And what does it look like in the low frequency limit as the frequency goes to zero? High frequency. What does a capacitor look like at high frequency? Looks like a short. I should say reactance, not resistance, but and what does our inductor look like? And it's just the opposite over here, right? C is our infinite resistance. And L is our 0. Okay, so what does this circuit look like? Let's redraw this circuit. We're going to replace the capacitors with wires, just a short. We're going to remove the inductor and not replace it with anything, leave it as an open circuit. And what does our circuit look like? Looks like that, right? So this is two resistors in parallel. That's going to give me, if I reduce this down one more time, R over 2. Okay. What does my circuit look like over here? In the high frequency limit, I do just the opposite. I replace the capacitors with open circuits. I just remove the capacitors and don't replace them with anything. And I replace the inductor with a short. So my circuit now looks like this. This is just two resistors in series. What's the purpose of this? The purpose is to, that you can make, the idea here is that you can see this circuit looks like it has 4 times as much resistance at high frequency than it does at low frequency. What can you do with that? Well, you can make something called a filter, a high pass filter or a low pass filter. You can make a circuit that has very low resistance at one frequency, but high resistance at other frequencies. And it allows one frequency to pass through, but not other frequencies. For example, in the walls of your house, you have the power, AC power lines. Those are very low frequency. That's 60 hertz. Okay, our power oscillates at 60 hertz, very low frequency compared to audio and video signals. Those are much higher frequency. If you have cables running in the walls of your house that pick up some noise from the wire, from the power, the AC power lines. They're picking up noise in the lower frequency, the AC power 60 hertz. If you run that signal then through a high pass filter that doesn't allow that 60 hertz to pass through, you can get rid of that 60 hertz noise and you get a cleaner audio video signal. So filters are kind of important in some respects. And this just gives you, this is not exactly a filter, but it just gives you an idea that, hey, this simple circuit looks like it has 4 times the resistance at one frequency than it does at another frequency. That's just trying to get you to see that. And that's all we're really going to do with AC circuits. So we're going to have situations where, you know, instead of having you solve for the current in every, in every device, or the voltage across every device at a specific time, I'll just ask for things like this. What is the volt? What do the meters read at high frequency? Or what's the current here at high frequency? What is it at low frequency limit? Things like that. So this kind of problem. Otherwise, it gets complicated, because in an AC circuit, what makes it complicated? Where's our A? Here's an AC circuit. In an AC circuit, there's a phase difference between when the different components hit their maximum voltages. So in other words, if I were to calculate the maximum voltage on my capacitor, the maximum voltage on my resistor, and the maximum voltage on my inductor, and I added them up, I would get more than the EMF that the power supply is putting out, the maximum voltage on the EMF on the power supply. How is that? Well, they don't all hit their maximums at the same time. They hit their maximums at different times. And that's why at any instant in time, we know that if we add up the voltage on the capacitor, the voltage on the resistor, and the voltage on the inductor, it has to equal the voltage that the power supply is putting out, right, at any instant in time. But they hit their maximums at different times. So if we added up the maximum values, we'd get more than the power supply is putting out. So you have to take those phase differences into account, and it becomes a little more complicated. Not too bad, but I just, we don't have enough time to deal with it, so we're not going to. Okay, so we're doing a very light, very simple conceptual treatment of AC circuits. The main points here are these. You kind of understand that AC circuits are like oscillators due to that capacitor and inductor, their property. And so if you kind of have that in mind, we do solve a lot of problems using energy and the fact that the energy oscillates back and forth between the L and the C in our circuit, the inductor and the capacitor in our circuit. And there are some interesting applications, like I pointed out. And then understanding how the different components affect the flow of charges at different frequencies. And really the two frequencies we care about are 0 and infinity, right? Those are the two frequencies we care about. And we've already been doing that with switches opening and closing in a DC circuit. When a switch opens or closes, that's kind of like an infinite frequency. But when it's been closed for a long time or open for a long time, that's like a 0 frequency, right, with the DC circuit. So we've already seen some of that. Okay. Oh, I wanted to show you this. I have which one do I want to do? Let's talk about RFID tags. Radio frequency ID. You've probably heard of these things. The fob for your car, for example, is an RFID tag. Where's my video? There it is. Okay. A lot of companies use ID cards like this, so you can scan them and get past locked doors. Or maybe you're familiar with a fob to get into your car. These are types of RFID. There's a coil of wire inside that gets energized by the card reader through electromagnetic induction. It provides power to that little chip, so no battery is needed. The chip sends a signal back to the card reader. Okay, very simple, very simple. You don't want to have to replace a battery in this. Like, for example, when you put a chip, they use these a lot with pets, right? You can have a little chip implanted in your dog's under the skin of your dog or cat. If they get lost, a vet can scan them. They all know that where they put the chips in the same place behind the neck. And you don't want to have to replace the battery in there, right? You don't want a battery, but the reader sends out an RF signal, right? That's some kind of a signal that's changing magnetic field. That there's a little coil of wire in that chip, and it gets energized just enough to send a little signal out. What is the signal? It's a number, right? And the reader reads that number, and they can identify your pet that way. They use these a lot in warehouses now. You can hang a big one on every pallet of stuff in your warehouse. You have a big pallet of stuff in your warehouse. You hang an RFID tag on it, and you input into your computer the number of that RFID tag and what's on the pallet. You have a whole warehouse full of pallets. Each pallet has an RFID tag. All you have to do is walk down the middle aisle with your reader. It sends out a signal, and all those signals come back, walk through the warehouse, and you've done an inventory. You've counted everything in your warehouse. Or you can have one on every single device and record it that way. RFID. Okay, and when we come back from our break, I'll show you one of my favorite demonstrations of the quarter. Sound good? Let's take a 10-minute break, and then we'll see my favorite demonstration. Okay, are we ready? One of my favorite demonstrations. It really ties a lot of the things we've learned together, and a cool application here. Let's take a look. If you've been to a museum recently, maybe you've seen one of these. It's a cassette. It stores information magnetically on that tape. The cassette goes into the tape player, and as that magnetic ribbon or tape passes across the pickup head, the magnetic signal is transformed back to sound. I'm going to play some music out of my phone. As soon as I plug in the headphone jack, it cuts off the music. But you can see my headphone jack isn't connected to a normal headphone. It's connected to this nail. That's an ordinary nail I picked up off the floor of my garage,
and the wire is wrapped around it and soldered together. I'm going to hold that nail over the pickup head on my cassette player and play my music from my cell phone through the nail into the pickup head on the cassette player and out that speaker you see right there. Let's listen.
Okay. First of all, the cassette tape that stores information magnetically, right? So you've got a whole series, right? You've got a north pole pointing up, a north pole pointing up, a north pole pointing down. And why does it have to move? Why does it have to move? You have a coil of wire here. There has to be a changing flux. So the magnetic poles are oriented on that tape, and the tape has to move across the pickup coil. That's not a very good. Has to move across the pickup coil. There has to be a change in flux. There has to be motion to generate a potential in that coil that you can then amplify and send to a speaker. What about a credit card? Nowadays, they have chips in them, but there's still a magnetic stripe on the back, right? How does that magnetic stripe work? There's a whole series of north and south poles. But when you use your credit card, when you use the magnetic stripe, not the chip, when you use the magnetic stripe, there has to be motion. You go to the gas station, what does it say? Insert the card, and it says remove it quickly. When you go to the supermarket, you have to swipe it. There has to be motion because the pickup coil it has to see a changing magnetic flux. As that card goes across the pickup coil, you have a pickup coil there. As the card goes across it, you have to get the change in flux, and it can detect that and convert that into a number. Every time there's a north pole pointing up, it's a 1. Anytime there's a south pole pointing up, it's a 0. It's a binary number, and it can convert that into a number. Yeah, you're generating an EMF in a little pickup coil, and then that can be amplified or something, detected. And microphones and speakers work very similarly. A microphone would have a membrane, maybe with a magnet on one side and a coil. And as you talk or sound hits it, it flexes a little bit. And the magnet on the back goes closer or farther away from the coil. And that can be detected and amplified, right? That's how a microphone works. And a speaker works exactly the opposite. There's a cone, right? Some kind of a cone shape on a speaker. And on the back of that cone, there's a magnet usually. And then there's a coil of wire here. So the signal goes in the coil of wire, and it drives this in and out, causes that cone to vibrate in and out, pushing on the air molecules. They push on their neighbors, they push on their neighbors. Eventually they push on your eardrum, and you perceive that as sound. So it's that cone vibrating in and out that creates the sound waves. How do you get it to vibrate in and out? You use a magnet on it, and you put a coil behind it. Okay, all of this stuff works in a very similar way. Now, headphones used to be really big. And then with the development of these rare earth magnets, that you can get really powerful, tiny magnets, these rare earth magnets, they could make headphones really small. They could make earbuds, right? They just fit right inside your ear. And that was because of the magnets that were developed that were tiny but strong. So what did I demonstrate for you with my demonstration? Instead of playing through a headphone, a speaker, so normally what happens? Current goes to the headphone through a coil of wire like this, creates a little magnetic field that causes the speaker to vibrate in and out and play sound into your ear, right? The headphone speaker. What did I do instead? I had that coil of wire come out, and I wrapped it around a nail. What's a nail? It's iron. That intensifies the magnetic field a little bit, right? Makes it a little bit stronger. And my coil of wire probably had a lot more coils than the one in the speaker, but that's okay. So lots of coils and that iron core to intensify the signal. And then instead of running the cassette tape across with the magnetic signal across the pickup head, I just held my nail up there over the pickup head on my cassette player, and then the cassette player then took that signal and sent it to the speaker. All right. So a lot of good applications. And a fun demonstration. All right, let's talk about one other thing we want to talk about with AC. Oh, before we get there, real quick, root mean square values. Root mean square values. So we know for a DC circuit and an AC circuit. In a DC circuit, our current is just at one value, right? We could call that the maximum value if we wanted to, but it's just one value. The current stays at one value. We could call that I max. But in an AC circuit, that doesn't happen, right? In an AC circuit, it oscillates. Something like that, right? And where this is I max. Right? Most of the time, the current is not at Imax. It's less than Imax. We need to come up with some kind of a way to average. What's the average current, right? Well, something like that. Well, what is the average current? What's the average of a sine wave? The average of a sine wave is 0, right? Half the time the signal is positive, half the time it's negative. The average is 0. So that doesn't really help us. What do? We do something called the root mean squared. We take the signal and we square it. That makes everything positive. Then we average it. Then we take the square root. So IRMS is I squared, averaged, square root. And for any sine or cosine function, we just divide by the square root of 2. The maximum value divided by the square root of 2. And this works for any sine or cosine function. Maximum value divided by the square root of 2 is the RMS value. We could do the same thing with power or voltage. So for power, we could say the average power is I squared R, and we can use the RMS value to get the average, right? It's a way of averaging an AC signal. In fact, we have a DMM we use, right? And in our labs, you've seen those used in the labs. When we use those with DC, when we connect them to DC, they just read the current, they read the voltage, right? It doesn't change. But there's an AC setting on those also. And when you set them to AC, what is it reading? It's reading the RMS value, the RMS value. Our power, 120 volts AC. What does that mean? Comes out of the wall. We plug in our appliances and things into the wall. We get 120 volts AC. What do you think that is? RMS or maximum? RMS value. So that means we're really hitting a maximum of about 170 volts. Okay, so now you know how the DMM works. It's when you use it for AC, it's doing this sort of it's a way of averaging a signal that would normally give you an average of 0 because it goes positive and negative. Sine and cosine functions spend half their time positive, half their time negative. You average them, you get 0. But if you square them all first and then average them and then take the square root, it's a way of kind of coming up with an average. We use the same thing with standard deviation, right? Standard deviation tells you how much each point varies from the mean in a data set. So you want to take the difference between each data point and the mean. But if you just average that distance, that difference, you'd get 0 because half your data points are above the mean, half your data points are below the mean. If you take the difference between your data points and the mean, you're going to average them and get 0. What do? You take the difference between every data point and the mean, you square it, you average it, and then you take the square root. That's what a standard deviation is. So we were kind of familiar. We've seen some of these things before. RMS value, and anytime it's a sine or cosine function, you get this 1 over the square root of 2 times the maximum value is the RMS value. That's just the way the math works out for sine and cosine functions. Okay, last topic. Transformers. This is the main reason we have AC power in our homes. Transformers. You can use a transformer to change the potential, to change the voltage of our signal. How do we do that? Well, we have to have a changing flux in one coil that feeds into another coil of wire. We use an iron core to get the magnetic flux from one coil into the other one. We usually draw it this way in our textbooks and things, but in actuality, they're built a little differently. I'll tell you about that. But this is our iron core. We have a coil over here on one side. And some kind of an input voltage. And we have a coil over here on the other side. And some kind of a, maybe a resistor over here, load. Usually call that a load resistor. So this is our primary. This is our input side. And this is our secondary, or the output. Over here we have V1, N1, right? N is the number of turns. Over here we would measure V2 and N2, I2. Okay, so that's how we designate the values with a 1 or a 2, input, output, primary, secondary, whatever you want to call them. But that's the nomenclature. And if this is ideal, if it's ideal, we have no energy lost in our transformer. All the energy that goes in one side comes out the other. No energy loss. And they're pretty good in the real world. I would say 90 to 99% efficient. They're pretty good. How do they get so efficient? Well, all the magnetic flux from coil 1 has to end up going through coil 2. And you could probably imagine, if this is what my transformer looks like, some of the magnetic flux generated by the first coil isn't going to make it through coil 2. How do we improve that? Well, most transformers have an iron core that looks like this one. And then the coil of wire is here. So we have V1 being generated here, and I'll use a different color. And then our pickup coil is here, right? If you stack them like that, then you get very good coupling of the magnetic flux. The power on the input side is IV, and the power on the output side is IV, but the 2's on the output side, right? Current times voltage is the power. If ideal, the power in is the power out. So we have I1 V1 equals I2 V2. And what we end up with is I2 is V1 over V2 times I1. Faraday's law, the voltage on 1 is minus N deflux dt, right? And the voltage on 2 is minus N2 deflux dt. And if we have really good coupling and all the magnetic flux generated by coil 1 goes through coil 2, which we have to have for an ideal transformer, then the rate of change of flux in coil 1 has to equal the rate of change of flux in coil 2. Does that make sense? Those have to be the same. So the voltage is going to be proportional to the number of turns. So what we end up with here is that V2 is N2 over N1 V1. It's the turns ratio. If we have more turns on the output side than the input side, we get more voltage out on the output side than we're putting in. The voltage is being stepped up. If we have fewer turns on the output side, we get a smaller voltage than we're putting in. The voltage is being stepped down. That's called a step down transformer versus a step up transformer. But you don't get something for nothing, right? You can't just take your 120 volts AC, put it through a transformer and get out 1,000 volts. You can, I shouldn't say it, you can, but the something has to give, right? What has to be the same on both sides? Energy or power has to be the same, right? You can't get more energy out than you put in. You can't get more power out than you put in. So that means that if the voltage goes up, what has to happen to our current? Our current has to go down. So I2 is going to be the exact opposite ratio. If the voltage goes up, the current goes down. Okay. What we want to do now is make this a little more useful. This is really important for a number of reasons. The main reason is that moving power from one place to another, electrical power, has losses, right? That you have to run it through wires. So they build a big dam outside of Las Vegas, Hoover Dam, and most of that energy goes to Los Angeles. So you have power lines running from Las Vegas to Los Angeles carrying the power. And you make those power lines as low resistance as you can, right? You make them out of the best resistor, the lowest resistance resistors, a wire. You make the wire big. You do the best you can to make the resistance as low as possible, but you can't make it zero. So there's some resistance. How do you minimize the losses as you send your power from Las Vegas to Los Angeles? You run it at the biggest voltage you can, because you need to get a certain amount of power to Los Angeles. That's the objective, is to get electrical power to Los Angeles. So power is current times voltage. If you run it at a really big voltage, you can run it at a very small current. And your current times I squared R is what your losses are in the wires as you're transmitting it to power, being dissipated as heat into the air as you're transmitting it through the wires. So the smaller the current, the less power you lose transmitting it, but you want to get the same amount of energy to Los Angeles. So you run it at a really high voltage, hundreds of thousands of volts, 600, 700,000 volts. They run the power from Hoover Dam to Los Angeles with a small current. You don't lose a lot of energy along the way because of that. Then you have transformers in LA that step that down eventually to smaller values, maybe to 50,000 volts that gets transmitted down the line behind your house. And then there's a transformer on the pole back there that steps it down to a couple of hundred volts, and that comes to your house. So those are the kinds of things. Transformers make it really nice for transmitting power over longer distances. Very important. The story is that Tesla was the big proponent of AC circuits, and Edison was the big proponent of DC because Edison owned all the patents on DC. He wanted to make a lot of money, and he was really pushing for DC power everywhere. And DC power can't be transmitted very far. That means you need lots of power generating stations all over the place, right where you're going to use the energy. He didn't care about that because he was going to sell everyone the power generating stations, right? He was going to make a lot of money off of that. Luckily, Tesla won out in the end, and all of our power is AC. It makes it really nice. It also makes it nice on the other end. You have 110 volts coming out of your wall, AC. So you can run it through a transformer and step it down to power battery operated devices. You can step it up to power the neon beer sign in your garage or the bug zapper on your front porch, right? You can step it up to do high power things. You can step it down to do things that to run battery operated devices. Let's talk about battery operated devices. We want to be able to run something that normally runs off of a battery, but what's the most expensive electricity in the world? Electricity from a battery, okay? Nowhere in the world do you pay more for electricity than you do when you get it from a battery. So you don't want to use that when you don't need to. You want to plug your device in, or you want to get rechargeable batteries. That helps reduce the cost a little bit. You pay for that convenience, right, of being able to carry that power around with you. Well, at home, you want to be able to either charge the battery or run a battery operated device off the cheap power that comes out of the wall. We need to be able to change our 120 volt AC signal into a much smaller voltage. I don't know, 9 volts, 10 volts, 5 volts, whatever your battery is, DC signal. So let's talk about that. First thing we need to do is convert. We already know how to change the voltage, right? We use a transformer. Transformer can change the voltage down. Now we have to change that AC low voltage signal into DC so we can plug it into our laptop, right? We use a rectifier. How do we do that? We use something called a diode. A diode is like a one-way valve for current. And the symbol is this, like a little arrow. The current can only flow in this direction. Let's take our AC. If we have some kind of an AC signal, source, and we have a resistor, what does it look like? The voltage across the resistor is the same as the voltage across the source, right? Looks something like this. Now let's add a diode. So we've got our source. What's it look like now? The voltage goes one way, and then it doesn't go the other way. It goes one way, okay? Looks kind of like this. It just cuts off the voltage in the opposite direction, the current in the opposite direction. Okay, we're halfway there, right? We've now, at least we only have current flowing one way through our resistor, but this doesn't look anything like DC. DC is a nice constant voltage. This is changing, but at least it's only flowing one way. We're halfway there. What can we do? We can add a capacitor. Well, we did an RC lab. What happened? So in this part of the cycle, the capacitor gets charged up. In this part of the cycle, the capacitor is not getting any voltage from the source, so it discharges through the resistor. And then it charges up again. So what we end up with over here is something that looks like this. It discharges, it charges, it discharges. It's like an RC circuit. Remember what that looked like from our RC circuit lab? If this is small enough, if that's small enough, it kind of looks like a DC circuit, right? That's called the ripple voltage. It changes a little bit, but if you can get that relatively small, that's kind of DC. Now let's include our transformer. And what do we get? One of those little black boxes that you plug into the wall. And use to charge your phone or something, right? Well, you use USB now, but what do you get in there? You get your wall signal, right? Comes to it. And inside there, there's a transformer. That's the symbol for a transformer. Something like this that converts that. And then it outputs it to your device, whatever it is. This is your, let's just walk through this real quick. This is your supply, right? Your from the wall outlet. This is your transformer. What kind of transformer? Step down transformer, right? To the voltage of the battery in the device. And then you get approximate DC, I'm calling it, right? There's a little bit of ripple in it, approximate DC. So the idea here is, what do you have to do first? Can you change it to DC first and then change the voltage? Is the order here important? Can we change it to DC and then change the voltage, or do we have to change the voltage first and then change it to DC? The order is very important. This has to be AC. If that's DC, how much voltage is being generated in the coil over here? Nothing, because nothing's changing. The coil has a constant magnetic flux. If this is DC, the coil has a constant magnetic flux in it. The other coil will have a constant magnetic flux through it. No voltage out. If the input isn't changing, right? Must be AC. Okay. So the order is very important. You can't change it to DC first. If you change it to DC first, you can't change the voltage. So if you want to be able to change the voltage, you have to do the transformer first. All right, let's take a quick look at what this looks like. I've got one here. That's not the one I want. Transformer.
We are all familiar with these little black boxes we plug into the wall and use to power our battery-operated devices, calculators, laptops, and things like that. Let's open it up and see what's inside. What do we expect to see? Well, we expect to see a transformer. This one has a leg that goes down the middle through that yellow coil you see. Actually, those are two yellow coils, one on top of each other. And my pen is tracing out the iron core. From this angle, you can see power from the wall goes in the plug, and it is connected directly to that top coil. The lower coil has outputs that go to our device. But something is missing from our little black box. Can you think of what it is? Stop the video and see if you can tell what's missing.
What's missing? What are we going to get out of this box? Yeah, it's missing the rectifier. We're going to get AC out, just at a different voltage that went in. There's nothing here to change it to DC.
Did you spot what's missing? If this little black box is powering a battery-operated device, it has to convert the signal to DC, direct current, because that's what batteries supply. But there's nothing here to do that. This is just a transformer. It takes in AC power at one voltage and puts it out at another voltage. Let's take a closer look at this black box and see what it's supposed to do. It takes in 120 volts AC and puts out 15 volts AC. That's very unusual for one of these black boxes to put out AC voltage. Let's see if this is a more common black box. The input goes in at the plug through those red wires to the top coil on the transformer. And the bottom coil sends its output to this circuit board. On this side of the circuit board, you see two diodes. On the other side, you see two more diodes. And in the middle, there's a capacitor. That converts the signal to DC. Let's take a closer look at what this black box is supposed to do. Input AC 120 volts, output DC 12 volts.
Okay. Let's take a look. Why 4? Why 4 diodes? Because 4 diodes are better. That's why. With one diode, what are you doing? You're losing half of your signal. You're just eliminating half of the signal, and you're only taking half of it and trying to convert that into DC. It would be much better if we could use 4 diodes. What we get is this kind of a circuit. We have our source, we have our transformer. Oops, you get the idea. And over here, you have diodes, one going in one direction and one going in the other direction. And over here, you have diodes, one going in one direction, one going in the other direction. So at some point in time, these two are connected together. And these two are connected together. So let's think about what's happening. We've got, when the current is going in this direction, what does it do? It can't go up to that upper diode. It goes through the lower one, and it goes out this direction to our circuit, to our resistor, our output. And then the AC source flips. I'll use blue. It flips and it sends the current out this side. Well, when the current goes out this side, it goes this way and it goes this way. So it always, the current always leaves through that side. It's always going the same way. It doesn't matter which cycle it's on. We didn't just cut off the voltage. The voltage looks like this. The voltage on the capacitor looks like this. Instead of just cutting it off, you see how that's much better than just losing half the signal? So instead of just losing half the signal, we're just flipping it so they're always positive. It always flows in the same direction. The other two are for the return path. The other two the diodes are for the return path. You need a complete circuit, right? I could keep going here with the arrows. The red one comes out there. It's going to go back in here, right? And the blue one will go that way, something like that. Okay. Questions? So transformers are used for stepping up voltage, stepping it up. If you need a higher voltage output, like to run a neon sign or something like that, or stepping it down if you need a lower voltage output to power a battery operated device. In conjunction with the rectifier, very handy devices, very handy. But the biggest benefit is that we can transmit power from one place to another without losing all of it. We can minimize the power loss during transmission by transmitting it at super high voltages and small currents, and then using transformers to step it down when you get to where you need to be. So I've got, I'll stick around now. There's no lab, but I'll come back at 12:15 and we'll run an office hour then, if you'd like. We've got our office hour at 4 o'clock. And then tomorrow, I've got my normal office hour at 4 o'clock. If you need any additional time, I could schedule something. Do we want a 1 o'clock something tomorrow at afternoon? Would that be helpful? All right. I'll send out an email with a link. So we'll do one in the afternoon tomorrow also. 1 o'clock probably. Does that sound good? Okay. Have a good afternoon. I'll see you either at 12:15 if you have some questions or want to come to an office hour then, or 4 o'clock, or tomorrow. All right. See you then.
Thank you, Professor.